Okay. So we will start with chapter 2. Here, basically, we are going to learn counting techniques, and then we are going to end the chapter with Bayes' theorem, right? So this course starts off very, very easy, right? At the beginning, you might get a bit, arrogant and say, "Oh, this is so easy," and phase out, right? But I promise you, after 10 minutes, it's going to get really mentally challenging, right? So you have to really focus during this course, because many concepts in this course are very, very confusing. So I'll talk about them. Even for well-known mathematicians, there has been a lot of arguments, over probability and statistics topics, right? So it's not just you who find some of the topics not very clear. It's just our minds, finds a lot of these topics tricky. Yeah. All right. Okay, so first is the concept of sample space. Sample space is a very easy concept. It means basically all possible outcomes, right? And we have two types of sample spaces. S can be discrete or it can be continuous, right? And you'll see that like a lot of this course is repetition. First, we cover everything with discrete sample spaces, right? And then we repeat everything with continuous, right? So it's very important that you have a good, you basically have a nice foundation in the early lectures of the course, because you'll find the following chapters trivial, right? They're just an extension of the previous chapters to continuous random variables. So let's look at a few examples. So we select a camera and record the recycle time of a flash. Then the sample space is all positive numbers, right? Because it can take any number for the flash for the flash to recycle and basically be ready for taking the next picture, right? So any time is the sample space, right? 1 second, 2 seconds, 0.5 seconds, any number. And suppose that it's known that all recycle times are between 1.5 and 5 seconds, right? Then our sample space is going to be this smaller sample space, right? This is much smaller than the previous one, right? And let's say that we want to make the sample space discrete, right? So we classify recycle times into low, medium, or high, right? Then our sample space is going to have three members: low, medium, or high, right? All possible outcomes. And in another example, let's say we are in the quality control and we want to say whether the camera conforms to minimum recycle time or no, right? In this case, the sample space is going to be yes or no, right? So very easy concept. Questions? So at any time, if you have any questions, you're most welcome to ask them. Yeah, sure. Go ahead.
Did you say that it will be on Moodle?
Yeah. So the lecture notes are going to be on Moodle for people who came late. So the lecture notes are going to be Moodle in two different formats: annotated and and blank. And also, I'm recording this. I don't think your voice is loud enough to be on the audio. We'll see. But basically, I'm recording these, and I'll post the video also on either Moodle or YouTube, right? And I don't check attendance, right? Of course, I want all of you to come to the class, but if you miss the class for any reason, you can basically watch the video later on, right? Or if you find the lecture very interesting, you can watch it later on, right? And you do actually later on, the course gets very difficult, so you do want to watch the lectures again. Other questions? Okay. So it's a very basically good practice to draw the sample space using a graph tree, right? Using a tree graph. So suppose that we are classifying messages as on time or late, right? So O stands for on time, and L stands for late, right? So let's say there's a communication channel, and every message can be either on time or late. And suppose that we are sending 3 messages in total, right? So in this case, our sample space is going to be all of them on time, the first 2 on time, and the third one late, and so forth, right? So this is basically S is the set of all possibilities, right? There's no possibility that's outside of this set, right? And we can show this using this tree. It's very useful if you learn this tree, because a lot of questions can be, made much more clear if you can draw the tree. So for message 1, we have 2 cases. It's either on time or late, right? And then if message 1 is on time, right, then message 2 can also be on time or late, right? And if message 2 is on time and message 1 is on time, then message 3 can be on time or late, right? So the way this tree corresponds to this set is basically we say on time, and on time. So this corresponds to the first member of this set, right? Nothing complicated. Right? But you see that this is a quite powerful method of basically laying out your sample space. It makes some very confusing problems easy to solve once you plot this tree diagram. Questions? Okay. So an event is a subset of a sample space, right? So any subset of a sample space is called an event, right? And we can basically have union of events because now we have sets, right? And we denote that as event 1 union event 2. We have intersection, which we denote that as event 1 intersection event 2. And we have complement, which we show with a prime, right? Complement means that all events that are not inside a certain event, right? So E prime means all possible outcomes that are not in E. So let's look at basically an example. Suppose that the recycle time of 2 cameras are recorded, and consider that only the cameras consider only whether the cameras conform to the manufacturing specifications or they don't conform, right? So we have basically yes or no for every camera, right? So every camera is classified as yes, conforms to manufacturing specifications, or no, it doesn't conform, right? Now, since we have 2 cameras, our sample space is going to be yes, yes, both of them conform. Yes, no, the first one conforms, the second one doesn't. No, yes, the first one doesn't, and the second one does. And no, no, neither one conforms, right? And now we define event 1 as an event that has where at least 1 camera conforms to the specifications, right? So in event 1, as you can see, at least one of these conforms to the specification, right? And you can check that event 1 is a subset of S. That's always the case. All events are always subsets of S. Any questions? Okay, so these are some abstract definitions. You will see later on why they are important, right? So in this course, you have to be a bit patient, and very soon you see that these abstract definitions come quite handy later on to formalize, real problems in real world. Yeah.
Can you repeat the difference between discrete and continuous?
Yeah, it's a good question. So discrete sample space means that the possibilities are discrete, right? For example, a camera conforming to some standards are not conforming, right? Or rolling a die, right? When we roll a die, the sample space is discrete because the numbers that we get are 1, 2, 3, 4, 5, 6, right? So this is a discrete sample space, right? Continuous sample space means, when the outcome is a real number, for example, right? For example, I ask you, how long does it take from now until the next student walks into the class, right? That's a real number because, it can be like 74.935 seconds, right? So usually time is a continuous random variable, for example, right? Unless if we discretize it ourselves, right? We say, oh, time, but only in seconds. I don't care about subseconds, right? Or like space, right? So I tell you that, oh, I have a machine that manufactures this piece, right? And the length of that piece is always a random variable because you're never certain that the length is exactly a number, right? So the length of, any piece is a continuous random variable, right? So later on in this course, we'll see like some distributions. And for example, one of them is the distance between two potholes on a street, right? That's also a continuous random variable because the distance is a real number. Did I answer the question? Yeah, okay. Okay. And now event 2 can be defined as no camera conforms, right? So this event is no. And now we add event 3, which denotes that an event that at least one camera does not conform, right? So event 3 means that at least one of them doesn't conform. So yes, no, no, why, no, yes, and no, right? So now what we can do is that we can do, we can do arithmetic with these sets, right? For example, we can find event 1 union event 3, right? So event 1 was yy, yn and ny. So basically the union is going to be, so basically, of course, all of the outcomes in event 1 are in the union. So basically first we write them down, right? So these 3, and then union event 3. So event 3 is this guy, right? So yn is already here, so we don't repeat, right? In sets, there's no repetition. Every member appears once, right? So we don't repeat this guy, right? And then ny is already here, so we don't need to repeat it. Nn is not here, so we have to write it down, right? So that's it. The union of event 1 and event 3 is basically all possible outcomes. So this turned out to be S. Right, the sample space. Right. So basically all I did is that first I wrote all members of event 1, and then I looked at members of event 3 and checked whether they are in the set. If they were, I didn't write them. If they weren't, I wrote them down. So the only event that wasn't here is NN. Right. And now we can do event 1 intersection event 3, right? So for intersection, we have to find the common outcomes, right? So we want both event 1 and event 3 to happen. So this is going to be, so yy is here, but is not here, right? Yn is here and also here, so yn. So this is here and also here, so yn. And then ny is here and is also here, right? And ny, right? So intersection is going to be yn and ny. And then complement means everything that's not in event 1, right? So complement of event 1 means that everything that's not in event 1. So we remember that S had 4 members and event 1 has 3 members. So event 1 complement is going to be only 1 member, right? Whatever that's not in event 1. So you see the answers here in the next slide. Questions? Okay. All right. So we can do the same exercise for continuous random variables, right? So suppose that we are measuring the thickness of a part, and the thickness is a positive number, so it's a part of R plus, right? And event 1 is if the thickness is between 10 and 12, right? So what I usually like to do for these cases is I like to draw, what is 10 and 12, right? So this is 10. And this is 12. So basically all numbers between 10 and 12, right? This is event 1. And then for event 2, I have all numbers between 11 and 15. And a full dot means that that number is included, and a hollow dot means that that number is not included. So event 2 is going to be between 11 and 15, right? So this is 11, and event 2 doesn't include 11, so between 11 and, suppose this is 15, right? So this is event 2, right? Now it's easier to answer, possible questions. If we want to find the union, it's going to be from 10 all the way to 15, right? So we can test how good the microphone is. So event 1 union event 2 is going to be from 10 all the way to 15, because 10 is covered in event 1 and 15 is covered in event 2, right? Now, the 10 part is more than or equal to, because this is a field dot, and 15 is less than 15 because this is an empty dot, right? Empty circle. Questions? Yep.
And there it says 12 is not included, but you put a full dot.
Say it again.
For the E1,
Yeah.
it says 12 is not included.
Oh, yes, thank you. Yes, thank you very much. Yeah. So if I had chocolates, I would throw you one, but I don't do that anymore. So yeah, very good point. So how can I keep? I don't know how I can change to eraser. I tried double tapping on the pen, but it didn't change to an eraser. Oh, there you go. Oh, no, don't go. So there you go. That's weird. Oh, I think I can't erase anything that I marked before, right? So I can't erase any of these guys. Anyways, so yeah, so this is an empty circle, right? Thank you. So still it doesn't change, right? So this is an empty circle, but still it's from 10 to 15 because event 2 still includes 12, right? And then intersection of event 1 and event 2 is going to be from 11 to 12 because that's the only common part. And then event 1 prime is going to be anything between 0 to 10 because the sample space was positive numbers only, right? So we don't have, we don't have the negative numbers. So anything between 0 to 10 or anything more than 12, right? So all numbers basically. So if this is 0, all numbers here, and also all numbers here is going to be the complement of E. Any questions? Yeah.
So the last symbol is anything outside of the intersection?
Can you say that again?
The last sentence.
Then E1 prime?
Yeah, it means anything outside of this.
Exactly, yeah. E1 prime means anything outside of E1, right? So I will draw it here again because I messed up the previous one. So this is 0, this is 10, this is 12, and this is event 1, right? This is E1, right? So event 1 prime means anything that's not included in event 1, right? So that's going to be, so first of all, S was R plus, right? So event 1 prime is going to be from 0, but 0 is not a positive number itself, right? So this is going to be a hollow circle all the way to 10, right? Now, 10 is also going to be a hollow circle because this was a full circle, right? And then everything more than 12. Now 12 was an empty circle, so here is going to be a full circle, right? So this down here is event 1 prime, right? Yeah, and one thing that you can check is that always, no matter what the event is, event 1 union event 1 prime is going to be S, right? So if you union those two, you're going to get the entire sample space. Yes?
For the last time, is it or and?
Yeah, it's or. Because and, that's a good question. So the question is this or and, right? So if it was and, then it's an empty set because there is no number that's both between 0 and 10 and is also more than 12, right? So that was a very good question. The question was, oh, this should be and because this set contains this and this, right? But math notation sometimes is a bit different than, like a common sense, which can be unfortunate. But basically, or means that it should be either between 10 and 0 or more than 12, right? If it was and, then it's an empty set because there's no number that's both between 0 and 10 and is also more than 12, right? Questions? Okay. So very often, it's much, much easier to solve these types of problems, union, intersection, using the Venn diagram, right? So in Venn diagram, we always draw a big rectangle for S, right? And then specific events are shown inside S as circles, right? So for example, we have A and B, and this is A union B, right? And this is A intersection B, right? And now we can do, more complex operations. For example, we can do A union B and then intersection C, right? So the way you have to do these is that, of course, you have to do them step by step, right? So first thing you have to do is, so this is A, B, and C, right? And then what you do is that first you do A union B, so this is A union B, right? And then you say, oh, what's the intersection of these and C, right? So the intersection is going to be this part only, right? So I don't recommend you do the whole thing at once, right? Do them always step by step. Like start from the parentheses and, move forward. Questions? Okay. And the last one, again, A intersection C prime, right? Again, we see that there's two operations, intersection and prime, right? So what you can do is that first you can do, one of the operations, which is the intersection. You just say, oh, this is A, this is C, right? And what's the intersection of A and C? This is the intersection, right? And then what's the complement of this? It's going to be everything that's not inside this intersection. So it's going to be this picture. So always do things, always break problems into smaller problems, basically. Questions? Okay. So we define two events as mutually exclusive if they have no common outcome, right? So this is the start. I told you the course starts to get tricky, soon. So this is the start of that. You'll see very soon why you find this concept tricky, right? So we say A and B are mutually exclusive if they can't happen together, right? And symbolically, we show that A intersection B is an empty set, right? So for example, if this is A and this is B, these two sets don't have any intersection, right? So these are mutually exclusive. Okay, so we are a bit ahead of the schedule, which is great. Okay, I already mentioned this, so we can move on to here. Okay. So we call two events, as I said, mutually exclusive if they have no intersection, right? So let's look at a few samples. So we throw a die, right? We define event 1. Let's say event A as number 1 comes up, right? And event B as number 2 comes up, right? Of course, these two events can't happen together, right? We can't have 1 and 2 at the same time, right? Or again, like another example can be I roll a die, right? And event A is an odd number shows up, and event B is an even number shows up, right? These two events are also mutually exclusive because they can't happen together, right? Or like turning left and right at an intersection, right? So you can turn left and right at the same time. What's not mutually exclusive is turning left and scratching your head, right? You can do both of them at the same time. Can anybody say another example of two mutually exclusive events? Yep.
Jumping and standing still.
Yeah, there you go. Yeah, so jumping and standing still. You can't do both of them.
Walking and running.
Yeah, walking and running. Yes, go ahead.
Turning off your car while you're in drive, you have to put on park, so you cannot put it in drive while you turn it off. Right?
Yeah, that's a good one. Yeah, so basically the answer is turning on the car and the car not being in the park mode, right? Yeah, that's can they happen together? No, they can't happen together. Yeah, they are mutually exclusive. Yeah, that's right. Yeah.
Being negative or positive.
Exactly, yeah. So if you get a test result, you can be both negative and positive, right? So there are many, you can think of many events that are mutually exclusive, right? So another example is you basically take a card from a stack, and let's say we define event A as getting aces, and we define event B as getting kings, right? These two events are mutually exclusive, right? But let's say I define event A as getting a heart and event B as getting a king, right? These two are not mutually exclusive because we have the king of hearts, right? Okay, so I think you guys are already familiar with De Morgan laws. So I mentioned that if you want to find A union B complement, right? It's better first to find A union B and then complement it, right? Another way is to use the De Morgan's law, right? So this is equal to A prime intersection B prime. Right? And a very similar rule applies to intersection, right? A intersection B prime is going to be A prime union B prime. Questions? Okay. And also we have the complement law, right? A prime prime is A, right? So if we complement something twice, we get the same thing. Okay. So now we move on to a very important part of this course, that you're going to need for the rest of this course, and they are the counting techniques, right? So there are three counting techniques: multiplication rule, permutation rule, and combination rule, right? But you'll see that if you master the first one, the other two are basically, they can be derived from the first one, right? The first one is in my opinion, is the most important one. So let's see when we should use, different ones. And by the way, for both midterm and final exam, I will provide a crib sheet, right? So you don't have to memorize any equations in this course. And you see that, for example, in the crib sheet, we say that multiplication rule, this is the equation. Permutation rule, this is the equation. Right. So all you need to learn is when to use, which one of these, when to use multiplication rule, when to use permutation rule, and so forth, right? You don't need to memorize any equation. And the idea is that now you can Google anything, right? We don't want you to memorize stuff because you can simply Google, what's the permutation rule. What's very important is you have to learn when to use permutation, when to use combination, right? The actual equation is not really necessary. Okay, so multiplication rule is basically is applied when I have to do an operation that consists of k steps. And basically, there are n1 ways of completing step 1. And the critical word here is and, right? And that's why it's in red, right? To complete basically this operation, I have to do all of these steps, right? That's very important, right? So I have to do step 1, and I have to do step 2, and I have to do all the k steps to complete that task, right? If I don't do one of these, then that task is not complete. Right? Then the total number of ways we can perform basically this task, which contains of k steps, is the multiplication of all of those numbers. N1, N2, all the way to Nk. Right? So this can be a bit confusing. Let's look at an example. So we want to design a website, right? And for the website, we have to choose a color. We have to choose a font. And also, we have to choose the position of an image, right? There are 4 colors that we can choose from, 3 fonts, and 3 positions, right? And the question is, how many ways can we, design this website? So since we have to do all of these, we have to do this, and we have to do this, right? The answer is just the multiplication of those numbers. Questions? Okay. Now, the next counting technique is permutation, right? So permutation is the number of ordered sequences of elements of a set, right? So let's look at an example before we see the equation. So so let's say that how many ways we can place 11 soccer players on a field, right? So here basically we are assuming that positions are important, right? Meaning that the goalie is the goalie, right defense is the right defense, right? So you can't ask just 11 people to go play wherever they want, right? We have to ask them, oh, you're the goalie, you're the right defense, and so forth, right? So basically, the way we can solve this problem is 2 different ways, and they give you 2 same answers, right? But it's very important that you learn both of them, because not all problems can be solved using these 2 methods, right? So the first method is I say that, I have 11 people, right? So this is person 1, right? How do I denote persons? So person 1, my drawing is not good, so I just write P, right? Person 2, all the way to person 11, right? So I have 11 people. So for person 1, I have 11 positions that, he or she can play, right? So person 1 has 11 positions, right? But in order to complete this task of, asking 11 soccer players to form a team, I have to also ask person 2 to, have a position, right? So there's an and, right? I have to ask person 1 to have a position and person 2 to have a position, right? So since there's an and, I have to multiply, right? How many ways are there that I can assign? How many places are there for person 2 to be assigned to? Exactly, 10, right? Because one of the 11 positions is already assigned to person 1, right? So person 2 has 10 positions, right? And I guess we see the trend now, right? The next person is going to be 9, and the last person, that's interesting, the last person doesn't have any options, right? So the last person has only one option. I shouldn't say any options. The last person has only one option because there's only one position left, right? And this number is defined as 11 factorial. right? Any questions about solution 1? Yeah. Yeah, so permutation, exactly, yeah, that's a good question. So permutation is when the order matters, right? So basically, to form a, soccer team, I have to tell this person to be the goalie and so forth, right? When the order matters, the answer is permutation, and yeah, it's going to be factorial, yeah. Yeah.
If you had 12 soccer players, would it be an exclusive situation?
Yeah, that's a very good question, right? And again, if I was throwing chocolate and if there was no COVID, I would throw a chocolate. So we will. So later on, we will go wild, right? So you'll ask many questions and I answer them. For now, we don't have the tools to answer that question, right? But I promise you, by the end of the class on Monday, any wild question that you have, you should be able to answer to, and we will answer them in class. Right? Yeah. So basically, the question was, what if we had 12 people and we wanted to form, a soccer team of 11 people, right? Hopefully, at the end of this class, maybe we can answer that. Yeah, it's a good question. Okay. Now let's. Can anybody guess what's the second way that we can solve this problem? So the first way, I first selected person 1. I told person 1, oh, you should play goalie, right? Person 2, you should play, offensive, and so forth. What's the second way I can, approach this problem? Yeah.
Position is not important?
Oh, no. So for this, so in this question, position is important, right? So I'm not interested in fact, if position wasn't important, there was only one way to form a team, ask all 11 players to play, right? So the answer to that question, if position is not important, is only one way. And we'll see today, why is one way, right? We see the equation for that, right? But no, we are still solving the same question where position is important. So what's the second approach? Instead of, starting from person 1 and asking person 1, yeah.
You can start from a position.
Exactly, yes. So again, that's a chocolate-worthy answer. So I can approach from the other end, right? I can say, oh, I have to fill up a goalie, right? So, this person fills up the goalie position, right? So basically, the way we can see this is I have 11 players, player 1, all the way to player 11. Unfortunately, positions also start with P. So maybe we say location, location 1. All the way to location 11, right? So basically, I have to, form, arrows between these two, right? So in the first approach, I started from person 1, and I moved all the way to person 11. In the second approach, I'm going to say, oh, for location 1, I have 11 options, right? So I fill up location 1, and then for location 2, since I've already selected one person, right? I have 9 people. I have 10 people now. So location 2 is going to be 10. Right? And so forth, right? Times 1, and this is 11 factorial, right? These might seem the same to you. They are not the same. Very soon, we'll see some problems that, we can solve them one way, but the other way becomes very, very hairy and very difficult, right? So you have to realize, midway through the problem, this is not working. Let me approach it in another angle. Yeah?
I don't understand the difference. What is
Yeah. So we have to, don't worry. So we'll see cases where, one of these cases doesn't work. We'll see them very soon, right? But for now, just, consider that in the first approach, first I started from person 1. I told person 1, you're a midfielder, right? I told person 2, you're a defenseman, and so forth, right? In approach 2, I started from the location. I said, first I fill up location 1, right?
Okay,
Then,
so P is not a position, it's person.
Yeah, exactly. So here, P again stands for person, and L, yeah, thank you. L stands for location, right? Yeah, so I didn't write P for position because, then it would have been confusing. But I think I still managed to confuse you. So, other questions? Okay. All right. So let's look at another example. So we have a set consisting of A, B, and C, right? And I want to find basically permutations, right? So different ways I can sort these, right? So different ways I can sort these three, these three characters are written here, A, B, C, and so forth, right? So again, to solve this problem, we can answer this, as follows. I can say that, to sort them, I have to find a place for A, I have to find a place for B, and I have to find a place for C, right? So these are my available places, right? So A has 3 options, right? B has 2 options because one of the places is already filled up by A, so times 2 times 1, right? Or I can think of positions, right? Again, like the previous example, there are 2 ways to answer this. So I can say to fill up position 1, I have 3 options. To fill up position 2, I have 2 options. And to fill up position 3, I have 1 option, right? So both of these are 3 factorial. Questions? Okay. So basically, this is the equation provided in the crib sheet, right? Number of permutations and factorial, right? Hopefully, you don't need this equation because it's quite easy, right? When we want to order them, we start from, different elements of the set, and we say, oh, this guy has 3 options, this guy has 2 options, and this guy has only 1 option, right? So you see that I didn't use the permutation rule, I used the multiplication rule, right? I said that I have to find a place for A, I have to find a place for B, and I have to find a place for C. Since there's an AND, I have to multiply. Questions? Okay. And by the way, factorial grows very fast, right? For example, 7 factorial, and 7 is not a big number, right, is 5,000. Right? So I guess like 50 factorial, I don't think your calculator will be able to compute 50 factorial. Right? That's really, really big. That has many zeros. Right? And by the way, that's the trick, lottery companies play, right? They say, oh, there's like, in total, 20 numbers that need to be ordered, right? And you say that, oh, if I pick this particular order, there's a good chance that I win. But, these numbers, for example, factorials, they grow exponentially fast. They grow very, very fast, right? So there are many, many ways you can order 20 numbers, for example, right? And in fact, that's the same way passwords work also, right? So, for example, if your password, right? So I'll have to write some things on the board because there's not always empty space on my slide. But let's say, you have a password that has 10 characters long, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So you have a password that's 10 characters long, right? And somebody's trying to crack your password, right? Basically by brute force is trying to log into your account, right? And let's say that each character can be, A, B, C, D, or it can be numbers, or it can be, those special symbols, right? So let's just make up something. So let's say there's 28 alphabetic characters times 2, because they can be, small or capital, right? 28 times 2 plus we have, 0 to 9, so 10 numbers plus 10 plus, let's say those special characters are 10. There's more than them, but let's assume there are 10. Right? So that's 56, and plus 20 is 76, right? So each one of these guys can be one of 76 options, right? So how many different passwords are there in total of 10 characters long? Yeah?
76 is 12, 10.
Exactly. So to basically, to create a password, you have to first decide what's the first, first letter, you have to decide what's the second letter, so there's an and, right? You have to do all of these, right? So first letter has 76 options. Now, for password, they don't say, oh, use A in the first character, you can't use A anymore, right? You can use A as many times as you want, right? So it's, the second guy is also 76, right? So all of them are 76. Does everybody see, or I write too small? Do you guys see? It's okay? All right. So I don't have much, like a lot of space, so that's why. So at the end, there's 76 to the power 10. Right? So, if somebody is, electronically entering your password, let's say, right? And every password to check, takes, let's say, 1 second, right? So that's 76 to the power 10 seconds, right? So 76 to the power 10 divided by 3,600 seconds in an hour. That's the number of hours that it takes to crack your password, right? Does anybody have a calculator? I'm curious to see what's this number. Or like times 24, that's the number of days that it takes to crack this password. Because there's 3,600 seconds in an hour and 24 hours in a day.
It's 7.4 to the 13th power.
To the 13th?
Yep, to the 13th power.
Okay. So that's 7.4 times 10 to the power 14? 13. 13, yeah. So 13, right? So that's this many days, right? And if we divide this by 356, so we basically cross two, like we eliminate 2 zeros from this and divide by 3. So that's 2 times 10 to the 11 years, right? That's this many years it takes to crack this password, right? So these numbers grow very, very fast, right? So that's what if the person can check 1 password per second, which is relatively fast, right? Like let's say even if you can do this faster, 100 passwords per second, still it's going to take 2 times 10 to the power 9 years, right? Very, very long time. So you see, that's why it's recommended to have long passwords, right? Because usually one of the common ways to crack passwords is to just brute force, right? Start from the beginning, 2 digits, 3 digits, 4 digits, and just grow, right? So if your password is long, then it's very hard to crack it, right? So that's the same, so basically the reason I did all of this is we don't have good intuition about big numbers, right? We have no idea how big is 76 to the power 10, right? So that's how big it is, right? If it takes 1 second to check every password, that's that many years. Questions? Okay. All right. And finally, by definition, we define 0 factorial as 1, right? So when we say by definition, it means that we don't want to prove it, right? But there are ways this can be justified, right? So I don't want to go into that, right? They are like a pure mathematics way we can justify, because, what is cool is that factorial is, so the way, like the things we saw so far is factorial is defined for, for integer numbers, right? But that's not the case, right? Factorial also extends to real numbers, right? There's a function that extends factorial to real numbers. We don't want to talk about all of that, but that number approaches to 1 as x approaches, that function approaches to 1 when x approaches to 0, right? So there are actually reasons for this, right? But, we just simply say, oh, by definition, 0 factorial is 1. Okay. Now, we want to do a subset permutation. So that's... so that was basically part of a question that was asked before, right? So we want to form a sequence of R items from a subset of N items, right? So basically, let's go back to our, to our forming a soccer, soccer team, right? So let's say form a team of 11 players from a pool of 20 players, right? So here it means that we can't select all 20 people, right? We only need 11 people for the soccer team, right? And again, position matters, right? So is important, right? So basically, position is important means that we have to specify who's the goalie, who's the right defense, who's the left defense, and so forth, right? So again, this problem can be solved using the both approaches that we saw before, right? So let's see how it basically plays out, right? So I say, okay, I have 11 positions, right? So to form a soccer team, I have to fill up my position 1, right? Position 1 can be filled up in 20 different ways, right? And then position 2 can be filled up in 19 ways, right? Because I have already selected one person, right? All the way to position 11. So when I reach position 11, I have already filled up 10 positions, right? So 10 people are already gone out of the pool of 20. So only 10 people are left, right? So times 10. Right, that's the answer. 20 times 19 times all the way to 10. Any questions about the first solution? Now, we can do some math tricks here, right? So we can, this is quite long to write, right? 20 times 19 times, 10. So we can instead write it, in a more compact way. So this is quite similar to 20 factorial, right? But it doesn't go all the way to 1. It goes to 10 instead, right? So basically what I can do is that I can say this is almost 20 factorial, but instead of going to 1, it only goes to 10, right? So I just divide it by 9 factorial, right? So this basically 20 times 19 times all the way to 10 is equal to 20 factorial divided by 9 factorial, right? Because the rest of the 9 factorial cancels the, not needed multiplications of 20 factorial. Is there any questions about why, this equality holds? Yeah?
Yes, sir. So how can I do it by the other way? Like just giving the player, each one has an element.
Yeah, that's a very good question. Yeah, that's the next, so I'm going to write it down here. But any questions about the first part? Okay. So now let's try to do it, the second approach that we said, right? So I have 20 players, right? Player 1, player 20, right? So let's say player 1, how many options do I have for player 1? So raise your hand. It's a very good question. How many options do I have for player 1? Yep. 11. So basically 11 positions in the team. That's almost correct, but that's not correct. Yeah. What is the one option? Say it again. No, but there are 11 positions, right? So when I pick person 1, right? How many options do I have for person 1? I can tell person 1 to be a goalie. I can tell person 1 to be, the offensive, So there's more than one option for person 1, right? One option means that I'm forced to do one task. There's no more option for me, right? So there's more than one option. Yeah, at the back? 20.
9 outside.
Say it again. Why 20?
So 11 on the field, 11 positions on the field, and 9 outside.
9 outside don't have any position. So if you're outside, you're outside. So can you fix your answer now? Yeah.
Would it be 12 because they have a chance of not being
Exactly. Yes. So that's 12. That's 12 options, right? Because player 1 can have any of the 12, any of the 11 positions, or not a position, right? So outside of the team, right? So player 1 has 12 options. Right? And then player 2 also has 12 options. Oh, actually, no. How many options does player 2 have?
11.
So how many people say 11? Player 2 has 11 options. Okay. How many people say player 2 has, what happened? Player 2 has 12 options. How many people say neither one or like both?
What was the first question?
Yeah, so basically, let me recap. So we have about 4 minutes, and I think we are going to end the class in a high note. I really like this. This is very interesting, right? And this is where the part, like questions become tricky, right? So player 1 has 12 options, and the 12 options are, goalie, offense, and so forth, all the way to no basically place in the team, right? Outside of the team, right? So let's write them down, So goalie, right defense, left defense, and so forth. And we have another, option here, outside. Right? So player 1 can go to any of these, so these are 11 options here. And there's one more option here outside of the team, right? So player 1 can be in either of these 11 or outside. How many options do we have for player 2 after, choosing an option for player 1? Yeah. Exactly, yes. It depends, right? Player 2 depends. Because if we assign player 1, for example, to the goalie position, then player 2 would have 11 options because one position is gone. But if we assign player 1 to outside of the team, then player 2 still has 12 options, right? Because outside of the team is more than one person, right? So we see immediately, oh, we're stuck. We don't know what to write for player 2. So this solution doesn't work anymore, right? So it's stuck, right? So it is possible to proceed, but it's very, very difficult, right? We have to draw a tree diagram, So you saw the previous solution, one line. If you do this, we have to spend an hour